All right, hi everyone, welcome back to chemistry. In this video, we're going to talk about ionic compounds. So we talked about ions, which we said are atoms that have either gained or lost an electron, and they, in doing so, have a charge now, either positive or negative. We call those positive ions cations, and we call those negative ions anions. So it turns out that we actually have things called ionic compounds, because what happens is positive and negative charges end up being attracted to each other, right? Just like we see with protons and electrons. So the positive and negative charges on our ions can actually be attracted to each other and create an ionic compound, or cause those atoms to bond with each other. Okay, so remember there's ionic bonds and covalent bonds, and ionic compounds happen due to ionic bonding. Yeah. Okay, so there are some properties of ionic compounds. Oh, I skipped over this. I was going to show you this. And let me move my mouse here. There we go. And get that out of the way. Okay. So I was going to show you this over here. If you zoom in, this is sodium chloride. So what is sodium chloride? Yeah, it's table salt. Yeah, this is what we put this on our food, right? So sodium chloride is a ionic compound that's sodium ions, more specifically sodium cations, right? Because sodium's in group 1A, so when it forms an ion, it's going to form an ion with a +1 charge, bonded to chlorine atom, or chlorine atoms with a charge, so chloride ions, right? We give it that IDE because it has that negative charge. And that's why you see that ending IDE there, is because that chlorine atom is now an ion. It's gained an electron, and now we call it chloride instead of chlorine. Where has it gained that electron from? Well, actually, it's specifically gained an electron from sodium, because sodium has given an electron to chlorine. And we'll talk about that more in a little bit. So kind of cool. All right. Now we can get back to properties of ionic compounds. So ionic compounds consist of negative and positive ions. And they have attractions called ionic bonds between positively charged ions and negatively charged ions, or cations and anions. Okay, they have high melting points. So what does it mean for something to have a high melting point? That means it takes a lot of heat, adding in a lot of heat before they start melting, right? And they're solids at room temperature. So salt, we know, is a solid at room temperature, right? We use it on our food all the time. We don't have to store it in the fridge to keep it in a solid form like we do other things. Okay, so here's some more. That's why I wanted to move on earlier, is because it's down here. I forgot. Okay, so here's a zoomed in look at sodium chloride again. So you can see your sodium metal here. And if you zoom in, you can see how large sodium atoms are compared to chlorine atoms. Remember your periodic table properties, right? I said atoms, but I mean ions. Well, the atoms as well. And when you look over here at sodium chloride when it's bonded together, you can see that it forms this structure that's really interesting looking, where we have one of our sodium ions bonded to one of our chlorine ions. And then it just keeps going on in that same structure over and over and over again. And what this is called is a crystal lattice structure. Okay. And you'll learn more about that in the future. So sodium chloride is more commonly known as table salt, and you can see the arrangement of those ions in an NaCl crystal, or a sodium chloride crystal. And that's why it has that kind of like crystalline look to it, if you look really, really close, like in this picture here. Okay, so chemical formulas of ionic compounds. So in a chemical formula, the symbols and subscripts are written in the lowest whole number ratio of the atoms or ions. So what is the lowest ratio that these two things bond in, right? So you could think of whenever we have H2O, for instance, water, right? We always see it as H2O. We don't see it as H4O2, right? Because we can reduce those numbers or we can simplify. A ratio of 4 to 2 is the same thing as a ratio of 2 to 1, right? So we always report our compounds with the lowest ratio, lowest whole number ratio of atoms or ions. Okay, so NaCl, we wouldn't see Na2Cl2 because that's the same thing as Na1Cl1. And, we also just write NaCl in that case, but just to kind of make it more clear there for you. Okay, so lowest whole number ratio. And in a chemical formula, the sum of ionic charges in the formula equals 0. Okay, and we'll talk about there's a reason that happens. And we'll talk about why that is. So when you have a positive charge and you add that to a negative charge, what do you get? Yeah, you get 0. They cancel each other out. Yeah. So the total positive charge equals the total negative charge, right? Our +1 ion is bonding with our -1 ion, okay? And they're canceling, those charges are canceling out. Okay, so, and the way that this works, let's look at this example a little bit closer. So what happens, remember I said with ionic bonding, one thing is losing electrons and another thing is gaining electrons. So what's happening is specifically your metal, remember metals like to lose electrons, is losing an electron or more than one, depending on what metal it is, right? We saw that. And your non-metal, remember chlorine is a non-metal, it's a gas at room temperature, is gaining that electron. So look at where sodium is on the periodic table. It's in group 1A, which means it likes to lose one electron to form a +1 charge or a 1+ charge. Okay, because why? Because it's losing a negative electron, right? Chlorine is in what group on the periodic table? Yeah, it's in group 7A. So how many electrons does chlorine need to be like a noble gas? It only needs 1. Yeah. So that's why we find that these two are bonding in nature. They both have something the other one wants. Sodium really wants to lose an electron, and chlorine really wants to gain an electron. So sodium's like, here you go, chlorine, take my electron. Looks like you really want it, and I don't want it at all. In fact, I'd rather not have it so I can be like the nearest noble gas, which is neon. Yeah, pretty cool. So it's going to lose that electron. Remember, we represent our electrons as dots. Why do we only have 1 on sodium? Well, sodium's in group 1A, so it has 1 valence electron. Yeah. Why do we have 7 on this chlorine? Yeah, because chlorine's in group 7A. Yeah, so we're representing those valence electrons. Okay. Okay, so this is before the bond, right? Before it bonds, and this is after. So after that sodium gives away its electron to chlorine, that sodium has a 1+ charge because it lost 1 electron, and it now has 1 more proton than electrons. Okay, and likewise, chlorine gained an electron, so it has 1 more negative charge than positive charges in its nucleus. Yeah. Okay, so when we write these chemical formulas, we like to write the formula with those subscripts. Remember that we have, H2O, here we have MgCl2. You don't see it in NaCl because they just bond in a 1-to-1 ratio, right? So we don't put this little imaginary 1 there, but it exists. So we want to be able to write those formulas without knowing them ahead of time, right? So if I gave you this side of the equation, you could find this side. And specifically, you could find this formula here. okay? So that you can eventually write your own chemical equations. Instead of when you're balancing chemical equations, I've been giving you those formulas. You need to be able to write those chemical formulas. So looking here, we have a magnesium. Magnesium's in group 2A, so it's going to lose 2 electrons to become a 2 plus charge, or a 2 plus, a magnesium ion with a 2 plus charge, I should say. And instead, if it wants to bond with chlorine, but each chlorine only wants 1 electron, that's okay, because it can bond with 2 chlorines, right? There's a lot of atoms around in our universe. So there's a bunch, where there's 1 chlorine, there's bound to be more chlorine atoms. So another chlorine is like, hey, I want an electron too, I'll take 1. And magnesium is like, great, here you go. I have 2 I want to give up. So it's going to have to bond with 2 chlorines. If it only bonded with 1, that chlorine wouldn't take that other electron. It doesn't want it. It only wants 1. Okay, so these are going to bond in a 1-to-2 ratio. But we have to show that in our chemical formula. Okay, and there's a trick for this, and I'll show it to you in a little bit. You're not going to have to like draw this whole picture out every time, or, you know, picture it in your head. Okay, so writing ionic formulas for ionic charges. So to balance the ionic charge in an ionic compound, the total positive charge has to equal the total negative charge. That's why these atoms are bonding in the first place. They want to be neutral. To be neutral is to be more stable. So if one thing wants to gain some electrons, the other thing wants to give away some electrons, they're going to bond and stay together because they both are attracted to the other one's charge. And because together they make a neutral compound. Okay, so if in this picture we have 2 sodiums bonding with 1, what's that? Yeah, that's sulfur. So bonding with 1 sulfur. So sulfur is in group, what is it, 6? So it has 6 valence electrons. Sodium is in group 1A, so it has 1 valence electron. So if sulfur wants 2 to get to 8, right, it's going to have to bond with 2 sodiums. And that's okay, there's lots of sodium around, so it will. And we're going to get a ratio of 2 sodiums to every 1 sulfur. And when that happens, what is sulfur's charge now? Because it hasn't just gained 1 electron, right? It gained 2. So if it gained 2 electrons with negative charges, its new charge is 2 minus, because it gained those 2 negative charges. Is sodium going to have a 2 plus charge? No, each sodium is going to have 1 plus charge, but we have 2 sodiums. So what you're doing here is, in order to calculate this out, you're multiplying the number of the atom that you have, or the number of ions that you have, by the charge on each individual ion. Let me say that again. You're multiplying the number of ions you have by the charge on each individual ion. Okay, so we have 2 sodium ions. Each has a 1 plus charge. Okay, and then we're adding that to our 1 sulfur, which has a 2 minus charge, and that is equaling 0. Why is that? Well, when we multiply the 2 times positive 1, we get positive 2, and negative 2 times 1 is negative 2. So we have a positive 2 and a negative 2. What's positive 2 plus negative 2? Well, that's just 2 minus 2, which is 0. Yeah, so overall, this compound, even though we have different charges that are not 0 in this compound, the whole compound on its own is neutral. Okay, because we have 2 pluses and 2 negatives. So those are canceling out, and we're getting a 0 charge as a whole. Okay? Or a net 0 charge, I should say. Let me actually leave that color coding there. Okay, so let's try this learning check. So select the correct formula for each of the following ionic compounds. We have Na plus, sodium ion, right? And then what's that O2 minus? What's that called? Is it oxygen? It is oxygen, but it's called oxide now, right? Because we drop the ending, and oxygen's it's a weird one because it has that kind of weird ending. We actually drop it to, let me show you. We drop all of this and replace it with the IDE ending, just like we do with chlorine, but chlorine's a little easier to see because it's got a very similar ending to IDE. We're really just changing these two letters, okay? But we're always having an ending IDE, only for anions, right? Only for the negative ions. We don't do that with cations, okay? Okay, so I just wanted, that's a little side note for you. All right, so what you're doing is you're selecting the correct chemical formula. Pause the video, try it out, and see, okay? Okay, so let's actually give ourselves a little space to look at this. So for number 1 here, just looking at number 1, we have Na plus and O2 minus. So if we have O2 minus, we have 2 minus charges, right? 2 negative charges, and we have 1 plus charge. So if we have 2 minus charges and only 1 positive charge, and when these bond together, remember, they want to be neutral. So how many sodiums do we need to have? Remember, because we can't just change the charge on that sodium. Sodium's in group 1A, it's going to form a 1 plus charge. So we can add more sodiums. Remember, there's lots of sodium around, right? So now we can say, okay, that's fine. I have a 2 minus charge on my oxygen, but I can just add another sodium atom, or ion, gosh, sorry. And now I have 2 sodium ions for every 1 oxygen ion. So how am I writing that formula? Well, I need to show a 2 here because I have those 2 atoms, or 2 ions. And I have, whoops, my O here because I have 1 oxygen atom. Ion, gosh, sorry you guys. Don't be like me. Call them ions if they're ions, if they're charged, okay? If they're neutral, it's an atom. If they're positively or negatively charged, they're ions. So erase that from your brain. But this is the correct answer, okay? 2 sodiums for every 1 oxygen. Okay, and you can check, right? If we have a total charge of +2 on this side of the compound, we have to have a -2 charge on the other side, and we do, right? Okay, I'll show you a trick in a little bit, but first let's go through these the long way, but there is a shorter way. But I want you to understand the concept first. So now we have aluminum 3+. That's the one that aluminum likes to form when it forms an ion, and then we have chlorine 1-. I guess I'll write it like they show it here. Chlorine -. So if we have an aluminum with 3+ charge, how many chlorines do we need to have to cancel that 3+ charge out? Because we can't just make this a 3, right? We can't do that. Chlorine, when it forms an ion, is always going to form a -1 charge or a 1- charge. Why is that? It only wants 1 electron because it's almost at 8. It's got 7 valence electrons, so it only wants 1 more. But that's okay. There's lots of chlorine around, so we can add more chlorine ions. How many more? Well, we started with 1 and I added 2. And the reason I did that is because I want the total on this side to be 3-. Okay, and I want that because I want to cancel out this 3+. Okay, so let me draw it like I did with the other ones, where I put the circle around it. Okay, so how many aluminums are bonding with how many chlorines? Yeah, so I have 1 aluminum bonding with how many? 1, 2, 3 chlorines. So my formula now, and there's not a space here, I kind of made it look like there's a space, but because they're bonded together, we don't have a space between them, okay? Now I have my chemical formula. That's what these are, that I've boxed here. Let me actually write that. in what, I don't know, green. So these are, whoops, chemical formulas. So if I ask you for the chemical formula of something, that's what I'm asking for. How do you write that compound as a formula? Okay. Okay, let's do this last one, and then I'll show you the trick. So 3, we have magnesium with a 2+ charge bonding with nitrogen with a 3- charge. Okay, this one's a little bit harder, but that's okay, we got it. So we have, let me get back to yellow here. We have magnesium with a 2+ charge and nitrogen with a 3-. How are we going to make it so these cancel each other out? Let's just try adding some things, right? I don't know, let's add a magnesium, because we can do that, that's legal. Okay, so now we have, what's our total charge on this side of the ionic compound right now? Yeah, 4+, because we have a 1 2+ charge and another 2+ charge, and that's going to give me 4+, 4 pluses. What about on the other side? We have 3-. So 4+ and 3-, do those cancel each other out? Nah, they don't. Okay, so let's go back to the drawing board here. So what if we add another nitrogen, 3-. Okay, now I have what? On the left side there, I still have my 4 pluses. How many minuses do I have on the right? Yeah, I have 6 now. Okay, but what if now I have 4 on the left, right? What if I add another magnesium? Now do I have, can these cancel out? Yeah, because, and you could also think of it, well, sorry, back up. you have 2 pluses, plus 2 is 6 total, right? 6 pluses on this side. And we have 6 minuses on the other side. So those are going to cancel each other out. Another way you could think of it, and if this helps, use it. If it doesn't help, that's okay. Draw it out like this. Is you could think of the least common multiple. Okay, so 2 and 3, I know that their least common multiple of 2 and 3 is 6. They both go into 6. 2 goes into 6 3 times. Okay, so I need 3 magnesiums. 3 goes into 6 2 times, so I need 2 nitrogens. Okay, so if that works for you, that's great. If it doesn't, ignore it and just draw it out like this. Okay, you will kind of just get used to that though. Okay, so I'm going to erase my little note here because hopefully that's in your notes now, so I can make room for the trick. Okay, so for the trick, let's actually scoot that up a little bit. I don't know why I drew it there. So here's some room for my trick. So I'm going to do each of these with my trick and to show you that it works. So again, when I first drew this, when I first did this question, I just wrote out the types of ions I had, right? That's what they're showing you here. So I have a sodium ion and an oxygen ion. And when sodium forms a charge, an ion, it's going to have a +1 charge, and oxygen is going to have a 2- charge. So what you can actually do is, now that you know how this happens, you can use this trick to make things faster. So what you're going to do is you're going to take, it's called the crisscross method. Sorry, my writing is pretty bad today. Okay, it's called the crisscross method. And what you're going to do is you're going to take this charge, which let me actually, just for our purposes right now, let me show it as a with the 1 there. So you're going to take this charge and you're going to bring just the number, not the charge, just the number over here. And that's going to be your subscript for the other atom. It'll make more sense in a second. Then you're going to take this charge and you're going to bring it over here under the other atom. Sorry, you're going to take the number associated with the charge, not the charge itself. So maybe I should actually fix my circle here and just show that we're taking the number that's associated with the charge. Okay, and we're going to pop those numbers. We're going to crisscross them and pop them under there. So you get Na, what? Well, I crossed over that 2. So Na2, what number goes next to O? Yeah, 1. Is that the same thing as this? Yeah. Yeah, pause the video, try it out, okay? I know it's kind of weird at first. I'm going to erase this one just because... Actually, you know what? I'll leave it there for now. No, it's going to bother me. Okay, it just looks weird. It looks wrong, so I'm going to get rid of it. But just know that that's how I got that, okay? Let's try it again with the next one. Okay, so aluminum 3 plus I started with, and then my other ion was chlorine 1 minus. Okay, so how am I gonna do this? So I'm gonna do a crisscross method, and I'm not taking the charge, right? If you put the charge down here, that would be, that would be a 2 minus and a 1 plus. There's no charge when these bond together, so that doesn't happen. Remember, this compound is neutral because those charges are canceling each other out. Okay, so I'm gonna get off my high horse there. So now we're gonna take this one, crisscross it over here. Okay, and we're gonna take this one and crisscross it over here. And we're gonna get what? Try it out. Al, what's the number on the right with chlorine? 1. Cl, what's the number on the left? 3. AlCl3. Is that the same thing we got? Yeah, it is. Okay, so this always works if you do it correctly. Okay, choo choo. Boom, 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 boom. Okay, all right, 3. Try it again. This one, try on your own. Pause the video, try it out. You're bonding these two species, right? And your goal is to write the formula, the chemical formula. Okay, if you wrote Mg, did we ever finish this one? Oh, I never wrote the final answer. Sorry. I wonder why. Huh. Okay, anyway, so if you wrote Mg3N2, you'd be correct. Yeah, because we're going to take this number, crisscross it over here. We're going to take this number, crisscross it over here under the magnesium. So we get Mg3 from here. And N2 from this guy. Okay, I didn't put the charges because this is a neutral atom. Neutral compound. Neutral compound, not atom. Okay. All right. So hopefully that kind of makes that a little bit easier for you, that trick. I'm going to scoot that all up there because I want just a little bit more space here. Okay. All right. So crisscross method. Okay, so now we have the other another thing that we have to look at, which is how do we name these ionic formulas, or how do we name ionic compounds? We just learned how to write the chemical formula, right? But what do we call this in lab? What do we call that in lab? So we're going to learn how to do that, how to figure that out. So and this is kind of something that you just start to memorize after a while, and you're going to want to kind of actively try to memorize how to do these, so practice it a lot. So for iodized salt, that contains Ki, which is potassium iodide, and that prevents iodine deficiency. Remember, we have that IDE ending. So which one of these is the negative ion? Which one's the anion? Just knowing this IDE ending exists. Yeah, it's got to be the I, because remember, the negative ion always has that IDE ending. Okay, so we add iodine to salt in order to prevent iodine deficiency. So kind of interesting, but you want to know how to name that, right? So when you're naming an ionic compound, the name of the metal is always written first. Okay, metal first. That's how I've been writing these formulas, how you've been writing them as well. Notice, the cation, the positive ion always comes first, and that's because which one's the positive ion? The metal. Yeah, metals like to lose electrons to form positive ions. Yeah. So the metal is always written first. It's just the convention. And is the same as the name of the element. So if you have sodium ion reacting with something like chloride, we don't change the name of that ion. It's just sodium. We call sodium ions the same thing as sodium atoms. It's just sodium. Sodium chloride. Okay, so metal first, and we just call it sodium. Or we just call it the name that you see on the periodic table. The name of the nonmetal is the first syllable of the nonmetal name plus that IDE ending. So the I meant to, actually, let's do the nonmetal in blue, I guess. So the nonmetal is the first syllable plus IDE ending. I guess we'll highlight all of that. Okay. And it's always written second. So sodium chloride. Sodium chlorine is not a thing, but sodium chloride, we know, has sodium ions bonded to chlorine ions or chloride ions. Okay, so, and then there's a space placed between the name of the metal and the nonmetal. So when we write, Na plus and Cl, sorry, I should show those bonded together, and Cl minus, right? We would write that as sodium chloride. Did I spell that right? Yeah. Oh, I didn't. That's what chloride. I knew it looked weird. Sodium chloride. Okay, and there's a space there in the middle, and we have that IDE ending. Okay. We've also got our metal first and our nonmetal with that IDE ending. This should technically have a little dash in there. Okay, so that's just the convention. That's how we name those ionic compounds, and that's just an example. All right, so let's do a learning check. So write the formulas and the names for the compounds of the following ions. Na, so you're going to do it like this, right? NaBr, NaS2, or S, and NaN. And then you'll do aluminum and bromine, aluminum and sulfur, aluminum and nitrogen. Okay, try it out, pause the video, see what you get. Okay, let's actually just do this together. I don't want to show you the answers yet. So for the first one, what's going to come first, sodium or bromine? Yeah, sodium's going to come first. Why? It's a metal. Yeah, it's a metal. How did I know it was a metal? Two ways, right? I could look on the periodic table and I could say, well, it's on the left of the periodic table. It must be a metal. Or I could look at that charge on it and I could notice that that's a positive charge. What kinds of elements like to form positive charges or lose electrons to be more positive? Those are going to be metals. Okay, so that's our metal. So let's go ahead and write that here. So what's this aluminum also? That's also a metal, yeah. Metal. Okay, so what are these negative charged ions or anions? Yeah, those are nonmetals. Non-metal. So first, I guess what I like to do is I like to categorize my metal versus my non-metal. Okay, because that'll tell me what compound I need to write first what element I need to write first. Okay, so Na comes first. So what's the name of Na? Sodium. Yeah, do I have to put sodiumide? Sodide? No, because it's the positive one, right? We don't change the metal. We don't change the positive ion. So it's just sodium. And then what is they didn't give us a ton of room here, did they? Let me actually write it. next to each other. Okay, so, and then how do I name that bromine ion? That's Br, that's bromine. It's in the group 7A. Is it sodium bromine? Like that? No. What is it? Yeah, sodium bromide. I'm pretending you're answering me. Hopefully you are. Yeah, sodium bromide. Yeah. Got that IDE ending because it's got that negative charge. Yeah. What about, let's keep going with sodium. So we already said sodium's the metal, so it's going to come first. And we know we don't change the name because it's the metal, right? So what goes here? Sulfur is what this compound is. So how do we get the ending IDE on there? Yeah, kind of weird. It's going to be sulfide. Sulfide. This actually specifies that you are taking the first syllable and then adding the IDE ending to that. So the first syllable, sulfur, sol is the first syllable. So we keep that. I guess we keep the F too. Yeah, some of these are kind of weird because they have kind of those weird endings. It's not as easy as it is with the halogens, right? Where we have like fluorine becomes fluoride, chlorine becomes chloride, sulfur becomes sulfide. Kind of maybe not as intuitive, but you'll start to get used to it. Okay, especially the more you hear it in lab as well. So sodium sulfide. Yeah. Okay. What about this next one? Sodium again, right? What's going to go next? Nitrogenide? Is that it? Nitride. Nitride. Yeah, sodium nitride. So nitrogen becomes nitride. Kind of weird, I know. Nitride. Just because nitrogide is really hard to say, or nitroide wouldn't really work, right? So, yeah. Nitride. All right, let's try the next metal. So we got, which comes first? This one or this one? Yep, aluminum comes first. Why? It's a metal. Do we change it to aluminide or alumide? No, because it's the metal. So we don't change that first one. So aluminum, we just write it like that. That's the name. And then what is the next part? Yeah, bromide. I'm going to write it down here, but just know that it's like you write them next to each other usually. Okay. Aluminum is going to be our first word again. What's our second word here? Yeah, sulfide. Or the second part of our name, I guess, for this compound, I should say. And then aluminum here. Aluminum, metal first, non-metal second. Non-metal is nitrogen. We're going to make that nitride because it's a negative ion. It's an anion. Okay. I hope that makes sense. But these they'll get easier as you keep doing them. So, something else to be aware of when you're naming these compounds. We've been so far really not talking about the transition metals. Remember, the transition metals are those metals in the middle of the periodic table. So starting with in period 4, we've got scandium, right? The step down, right? The shorter columns rather than the tall columns. We've really only been talking about tall columns for this entire chapter. But transition metals also do form ions. They are metals, right? So they're going to form positive ions. And except for some of the transition metals, like this one, and this one, they'll often form different, they can form more than one positive ion. So it's not like with sodium, where whenever sodium forms an ion, we know it's going to form a 1+ ion. It's not like that with transition metals. With many of the transition metals, they're going to form what's called variable charges. So it depends on what they're bonded to, what kind of charge they're going to form. So the way that we show that when we're naming these compounds to show what type of ion we have for those transition metals, those metals in the middle of the periodic table, is we give these little Roman numerals next to the name of the metal, okay, or the name of the transition metal. And those Roman numerals are going to show us what what cation we're forming. Okay, so look at this, just this copper for now. So copper likes to form two different types of charges. It can form a 2+ charge or a 1+ charge, just depending on what it's bonded to. So when it forms a 2+ charge, we give it the Roman numeral 2. And when it forms a 1+ charge, we give it the Roman numeral 1. If you just put copper, like let's go with an example like copper sulfide. Or let's go with chloride, actually, just because we've just been talking about chloride a lot. So copper chloride forms what charge? Or I'm sorry, chlorine forms what charge when it's an ion? Yeah, it forms a 1- charge. Yeah, it's in group 7A, it wants 1 electron, so it forms a 1- charge. So copper's like, well, I could do a 2+ charge, or I could do a 1+ charge. What do you think it's gonna be in this compound? Yeah, it's gonna be a 1+ charge. Why? So these can cancel out. Yeah. So when we write copper chloride, we don't just write it like this, because that doesn't show us what charge that copper is. It doesn't show us what kind of copper ion we have, and it does make a difference. So what we need to do is we need to write our Roman numeral here. If copper is forming a 1+ charge, what number goes in here? What Roman numeral? Yeah, 1. Yep. Just to show that, hey, we have copper 1+ in this compound. Okay, so when you look at a label in lab, if you're dealing with copper, you're always going to see that, that little Roman numeral. Okay, so in this example, we have manganese bonding to, that's what Mn is, okay? Manganese is a transition metal. You'll find it in the middle of the periodic table. It's in group 7B, okay? And it can form different charges. Fluorine, though, fluorine always forms what charge? Yeah, always forms a -1 charge. Because it's in group 7A, it's right next to the noble gas, neon, so it just wants to gain 1 electron. It's not really going to want to gain any other electrons because it only needs 1. So what we can do is kind of do some puzzle solving. If we have 2 of these fluorines, if we have 2 of these fluorines, and they have a 1- charge each, our total charge on that side of the compound is 2-. So what does the charge on Mn, on manganese, have to be if we have a 2- charge on this side? Yeah, it has to be 2+, right? Those two things need to cancel out because remember, this entire thing is neutral. If it wasn't neutral, and you will see this in just a little bit, you would see a charge somewhere outside of that compound. We'll talk about that in a little bit. But because you don't see anything, we assume it's neutral. And it is. So now we know we have to have a 2+ charge on that manganese. So that now we know what Roman numeral we'll need to use. Okay? You can practice this learning check and I will show you the answer. Okay. Let's scroll down to the answer here. We want the answer. Okay. So, yep, there's the answer. Check your work. If you didn't get it right, go back, look at your notes, see what you might have done wrong, okay? All right, I'll see you back here for talking a little bit in a short video about polyatomic ions.